Hello, everyone. I'm Rishabh More, graduate student at Purdue University, and in this talk, I'll be presenting results for the settling motion of spheroid-shaped particles in a density stratified fluid. I performed this research along with collaborators Mehdi and Professor Luca Brand, and my advisor Arezu Adekani. So the upper, so to give a brief motivation, the uh, uh, upper layers of oceans usually observe a vertical variation in density, which can be due to vertical variation in temperature or salinity. And these layers are host to a bunch of different entities like microorganisms and fishes and submarines and or marine snow particles and or nutrients. So if we just look at uh, phytoplankton, uh, they actually come in a variety of shapes other than spherical. Um, the most common shapes are disc-like flat shapes or rod-like elongated shapes. Um, in addition, the marine snow particles are also not exactly spherical, and they are kind of elongated. So it is very important to understand how this anisotropy affects the motion of these particles in a stratified environment. Also, the atmospheric air observes a density stratification similar to oceans, and these layers also have either pollutants in them or bunch of different entities which can be of different shapes. And if we go to a cosmic level, then this photograph shows a basically a bubble inside the gas, and this bubble also experiences a variation in the density. So it is basically uh, an interesting problem to look at. So to this end, we solve the Navier-Stokes equations for calculating the flow field, and in addition to that, we solve the advection diffusion equation for the temperature, uh, which basically gives us the variation in the density. And we use the immersed boundary method to model these particles, and we run simulations for two different types of particle. One is oblate spheroid, for which the aspect ratio is smaller than one, and the other is a prolate spheroid, for which the aspect ratio is larger than one. And we also track the orientation of these particles, and we define the orientation as the angle made by their major axis with the vertical z-axis, and z-axis is the direction of gravity as well as the stratification. The important dimensionless numbers are the Reynolds number and the Richardson number, which basically quantify the inertial and the stratification effects respectively. And one more important term to note is basically this baroclinic vorticity generation term, which comes in the vorticity equation because of the misalignment of equal density lines with the z direction. Yeah, so the first important result is regarding the orientation of these particles. In a homogeneous fluid, both the oblate and a prolate spheroid settle uh, in a final orientation such that their longer side is horizontal. But the situation is completely different in a stratified fluid, and what we observe is uh, the horizontal broadside on orientation is not stable, and both the oblate and prolate spheroids reorient and eventually settle orientation in an orientation such that their longer side is parallel to the direction of gravity. And if we basically look at the velocity evolution along with the orientation evolution, we what we observe is that this onset of reorientation is associated with the magnitude of the settling velocity falling below a particular threshold. So as soon as the velocity falls below this threshold, uh, the the spheroids start reorienting. And in addition, the velocity evolution plot tells us that as the particles start settling from a zero initial velocity, it achieves a peak velocity, after which, because of the stratification effects and the drag, it decelerates and eventually stops moving when it reaches its neutrally buoyant position. Um, to quantify the effects of stratification on the velocity, we plot the peak velocity for both oblate and prolate spheroid, and what we observe is the peak velocity decreases as we increase the stratification, and this is expected because with increasing stratification, the uh, isopycnals offer more resistance to their deformation, and as a result, uh, the the spheroids experience more drag, and which basically leads to a reduction in the peak velocity. We also plot the time for the onset of velocity, the time at which the settling velocity of the particles fall below the threshold required for reorientation. And what we observe is this data falls on a single curve, which is basically inversely proportional to the Richardson number for both oblate and a prolate spheroid. So this tells us that as we increase the stratification, the spheroids start reorienting at an earlier time, which is inversely proportional to the Richardson number. To explain why the reorientation instability sets in, we basically look at this baroclinic vorticity generation term. This term is not present in a homogeneous fluid and present in a stratified fluid because we have this misalignment of density gradient. So what happens in a homogeneous fluid is that as as the particle uh, settles, it accelerates and reaches a terminal velocity. And once it reaches a terminal velocity, it experiences vortex shading, which basically takes place alternatively at either edges. And because of that, it basically settles in an orientation such that its broadside is horizontal. But what happens in a stratified fluid is that initially the particle accelerates, which can be inferred from expanding of these vorticity contours. Uh, and as it accelerates, it topples from this initial edgewise orientation to a broadside on orientation. But as it happens, the isopycnals are basically deforming, and once the particle reaches the peak velocity, the isopycnals are deformed so much that they resist any further deformation. And once that happens, the isopycnals try to return to their original neutrally buoyant position. And because of that, the particle start to decelerate, which basically uh, can be inferred by this reduction in the size of the vorticity contour. And as the particle decelerates, this vorticity generation around the particle due to the deformation of isopycnal remains asymmetric, and this green thin line, which basically separates the regions of positive and negative vorticity, predominantly remains on one side of the spheroid. Uh, and because of that, there is a constant torque which the spheroid experiences. Uh, and once the velocity of the particle falls below the threshold, the inertial effects are not not enough to basically overcome the stratification effects which are trying to reorient these particles, and because of that it basically reorients once its velocity falls below the threshold. The same thing happens for a prolet spheroid, and this vorticity generation remains asymmetric, because of which it basically finally reorients and attains an edgewise orientation. Next, we also compare the settling trajectories of these spheroids in a homogeneous and a stratified fluid, as shown here. So the blue line here is the trajectory of an oblate spheroid in a homogeneous fluid at different Reynolds numbers. And as you can see, the settling path is oscillatory for higher values of Reynolds number. Um, and as we introduce stratification, we observe that these oscillatory paths are eliminated because of the stratification, and and the trajectory is basically similar for all the Reynolds number. So and this is basically summarized in this nice figure here, where we plot the trajectory in red and along with the settling velocity evolution, and looking at this figure, we divide the settling trajectory in three distinct regimes. The first regime is when the particle settles in a horizontal orientation like this, say similar to a homogeneous fluid. But once its velocity falls below the threshold at which the reorientation instability sets in, it starts to reorient, and as it reorients, it basically deflects in the horizontal direction. And in this regime, it attains a quasi-steady velocity, which basically uh, continues till it is completely reoriented to an edgewise orientation. And as it finishes reorienting, then it velocity falls a lot rapidly and becomes zero, and it stops moving. The similar thing happens for a prolet spheroid as well. Basically, stratification eliminates the oscillatory path. But in a prolet spheroid, we only observe two distinct regimes. The one is homogeneous fluid-like regime where the particle settles in a horizontal orientation, and once the velocity falls below the threshold, it starts to reorient and gets deflected in the horizontal direction until it reaches a final orientation such that its its longer edge is along the direction of gravity, and and finally it stops at its neutrally bound position. Yeah, so that's it for this talk, and this slide summarizes all the conclusions of this study. Thank you.